Okay, so this is the worksheet for AP Calculus 7-2. Today's date is Tuesday, January 7th, 2020. This is the key. So remember that if I take the second derivative and take the integral, I go to the first derivative, take the integral again, I get to the original function. Acceleration, the integral of acceleration is velocity, the integral of velocity is position. And I guess I can say that this is position right there. Okay, so using correct units, we're going to explain the meaning of this in the context of the problem. So again, you should always be saying total change in whatever. So this is going to be, maybe it would be more efficient if I typed my answers. I've used this technology, but I don't know if it makes it look better or worse. Let's use blue. So this is going to be the total change in position in this case, because the integral of velocity is position. And then position is measured. You should have units on both of them. I think I forgot to do that in the notes too. So it should be in meters from 20 to 40 seconds. Perfect. That's it. Moving down here, using correct units, explain this one. Okay, so this one is going to be the total change in, okay, so I have velocity, integral of velocity is position. So total change in position. What are we in? We're in feet now. In feet from, so 10 to 70, so 10 to 70, and we're dealing with seconds. Same thing yet again. This is going to be the total change in, so integral of velocity is position. So we're in miles now. From the bounds are 0 and 40, so 0 to 40, and our units are minutes. Should I be adding periods to these? Does it matter? Okay. Coming down here, using correct units, explain this one. So another explain. So this is going to be the total change in, okay, so integral of velocity is position. From, position, in, okay, what are our units of position? So we were in, I think this is feet here. Feet per second is kind of hard to see. I'm going to say in feet from, our bounds are 0 to 50. From 0 to 50, and our units are now seconds. Done. Moving down here. Okay, so now we actually have to do some math. So I need to find the integral between 0 and 24 of velocity. This is a graph of velocity. Okay, so I'm just finding the area. This is where I have to pull my pencil back out and say, okay, I'm going to split this into shapes. Let's make straight lines here. Let's do blue lines, sure. A shape there, a shape there. Okay, so this is a triangle. It's 4 here by, it goes up 20. So this is a 4 by 20 triangle, so multiply those 80, and it's half, because it's a triangle. Half of 80 is 40. I'll circle my areas. This is 4 to 16, so that's this total distance down here is 12, and then height again of 20. 12 times 20, and it's the same thing as 12 times 10, and then double it, right? So 24, and then double it, 240. And then 16 to 24, I go 4, and then another 4, so this length is 8, and again by 20. So 8 times 20 is 160, divided by 2 is 80. Okay, we found the area of all of those. Just add them up. So this is going to be equal to 40 plus 240 plus 80, and we get 360. Always remember units in this case. So the integral of velocity is position. Position is just meters. M for meters. And box it. Make my box a little bit bigger. Using the correct unit, explain the meaning. Okay, so explaining the meaning. Coming down here, this is going to be the total change in, okay, integral of velocity of position. Position from 0 to, position, remember units here, in meters from 0 to 24 seconds, because it's time is in seconds right here. All right, perfect. Moving on. We have explaining the meaning for A, so I'll come down here and I'll label this, maybe here, we'll say for A, the total change in, okay, so acceleration turns into velocity, and that's in feet per second from 0, because that's the lower bound, to 30. To 30, and our units here are seconds. Okay, yeah, this is where I messed up on the notes. I should have had a three-way table like this with, 3 velocity, acceleration, time. And then for B down here, we need to find the exact value of that. So I'm going to derive it again. I know that you're already probably thinking, oh, that's pretty easy. It's just do position 1 minus position the other one. Okay, so I'm really doing the integral from 0 to 30 of acceleration with respect to t, so dt. Integral of acceleration is velocity, so I have velocity now with respect to t, and evaluation bar because it's a definite integral between 0 and 30. Okay, when I have evaluation bar, I plug in the top, or the upper bound, so it's going to be v of 30, ooh, that's a bad 3, v of 30 minus v of 0. And you could have jumped straight here if you memorized kind of the formula. How do you find the exact value? You take the integral and then plug it in, right? So 30 is a position. This is v, or sorry, the velocity is going to be negative 14. So negative 14, and v of 0, that's negative 20. So minus a negative 20. The double negatives, that turns into a positive, and that's going to be positive 6. Our final answer here is equal to 6, and don't forget our units. We're talking about velocity here because it's the integral of acceleration, so our units should be in units per time or feet per second. It even tells you the units right there. You can just copy down feet per second and box it. All right, table gives you velocity. Which of the following could be a graph of the position? Ooh, this one's going to be interesting. Well, I know if I'm trying to get from velocity to position, velocity on a graph of position is slope. So I can say that v on a graph of, I guess, x is, and then the keyword here, I'll do it in red, is slope. So I'm looking for these slopes. So I have a slope of -1, a slope of 2, a slope of 3, a slope of 0, a slope of -4. Well, the one that jumps out to me is a slope of 0. I know that's a horizontal tangent, right? Slope of 0 at 3. So I'm going to go over 1, 2, 3. That's not a slope of 0. No, okay. I should switch back to blue here. That's not 0. Slope of 0, no. Slope of, okay, so that has a slope of 0. 1, 2, 3, so that one's good. 1, 2, 3, that's not a slope of 0, and 1, 2, 3, okay, that does have a slope of 0. So it's between C and E now. What other distinguishing features are there? Well, I guess I'll just start with the first one. I have no idea. At 0, I should have a negative slope. So which one immediately starts jumping down? Well, C starts going down, and E starts going down, so that doesn't really help us that much. At time is equal to 1, the slope is 2. At time is 1, the slope is 2. That's positive. At time is, ooh, check that out. At time equals 1, the slope is very much 0 there, so it's not E. Correct answer here is C. Just judging off of the slopes. All right, we're on to the next problem. I guess I should be numbering these. I'm pretty sure that this last number, this is probably number 7. I should maybe label these in the future. This is number 6, 5. Sorry for doing this right in the middle of the video. 4, 3, 2, and that was number 1. All right, so we are now on to problem number 8. It starts at rest, and it starts there at 2, 0. Okay, well, I'm immediately looking at these graphs. I'm like, well, some of them are at 0, 2, and some of them are at 2, 0. So 2, 0 means you have like a start here. That these are not, they don't look right because they're at 0, 2. So automatically, I think we've eliminated all of them except for C and D, just knowing where 2, 0 is on the graph. And it moves along the x-axis with a constant positive acceleration for time is equal to 0, which of the following could be a graph of the distance of the particle as a function of, oh, okay. So I maybe need to undo those. A distance from, okay, so if I'm starting at 2, 0, the distance between the x-axis. So if I'm thinking of a sketch here, I do start there, and it's these graphs represent the distance from the origin. So if I come up here, I'm going to do that distance. If I come here, it's that distance. If I come over here, it's that distance. What is this diagonal length, maybe a horizontal or vertical length? What is that distance from the origin? Well, I know that I start at a positive amount. So if I start at a positive amount, that actually does eliminate C and D, interestingly enough. It should be A, B, or E. So I start with a distance away from 0. I know that because I started farther away from 0. And then moves along the x-axis with a constant positive acceleration. So these all represent distance, or you can kind of think of this as position from the function or of the particle. So these are all graphs of distance or position. If we're talking about acceleration on a graph of position, acceleration, this is really talking about concavity. So if it's always concave up, then I should be looking for concave up. That's clearly concave up, so it could be A. That is not concave up nor concave down, so this is no concavity. And E similarly has no concavity. So the only answer is A. And I think I got that one wrong last time, which is interesting. Let's go on to number 9. The position of the particle is that guy. So this represents position. I can kind of think of this as x of t. Maybe I should make my t a little bit curly. X of t is equal to negative 5 curly t. That's a way too curly t squared. I'm looking for the average velocity. I'm going to underline that because that's the key word. So you have to know the definition of average velocity. And you still take the integral of velocity. By the way, the average of anything is the integral of that anything. If I was looking for the average acceleration, I'd take the integral of acceleration and then always do the 1 over b minus a type of thing. If I'm doing bounds from a to b, don't forget my dt to be formal. There it is. There is the definition of average velocity. You guys want the definition of average acceleration? Change that out for an a. Change this to an acceleration and you're done. That's the average acceleration now. So when I actually fill this thing in now, this is going to turn into 1 over 3 minus 0 because our time constraints are between 0 and 3. And that's going to be the integral from 0 to 3 of our velocity function. We don't have velocity. Interesting. So I'm just going to leave it as velocity for now. Vt dt. That's as much as I can do. They didn't give us velocity, right? But I know that eventually if I take the integral of velocity, I'll get position. And hey, I have a position equation right there that I can sub in. So taking the integral here, that's going to be position, right? Antiderivative of velocity is position. And then evaluation bar, and technically it should be divided by 3 because I still have that fraction, right? Evaluation bar between 0 and 3, and that turns into x of 3 minus x of 0. And if I was being very formal, I could copy that on that 3 minus 0 all the way over here, and you'd get that same formula that we had, 3 minus 0. But it's really just 3 right on the bottom. What is x of 3? What is x of 0? Well, we have this formula up here that we took from right there. 3, plug that in. 3 squared is 9. 9 times negative 5 is negative 45. So I have now, I'll come over here, negative 45. That's the first one. Minus, and then what happens when I plug in 0? 0. All over 3. So the answer here is negative 15. I'm thinking units now. What would the units be here? So I'm looking for average velocity, so my units should be in for velocity, and it doesn't say anything, so I don't need to worry about it. That's the correct answer. Done. Typically it would be units per time, but there it is, negative 15. Let's move on to number 10. This is clearly a calculator problem, and it didn't have any calculator next to it, no symbol. I apologize for that. That is my bad. This is a calculator problem. I'm sure if you're watching this video in the far future, I probably fixed all this. This worksheet looks really, really old. Let's pull up our calculator. So I'm not able to get my my new calculator working for whatever reason. So I'm going to use my old calculator. I'm pretty sure it converts really easily. So I have a velocity function, and I need to find the average velocity. So let's go ahead and write some things down first. What is average velocity? Average of anything is the integral of that anything. Average of that anything. So average of velocity is velocity, and then don't forget to divide by time. So this is going to be 3 minus 0 from 0 to 3, and then I'm going to plug in for that vt. That vt is really e to the power of t plus t e to the t. Type that in your calculator. Go. So it looks a little bit wonky on the older calculators, I know. So this is going to be e. So I do second natural log e to the power of that t, in this case x, and parentheses plus and then I'm going to do that variable x in this case, and then I don't need to do times, because if I squish them together, they know that they're being multiplied. E to the power of t. Ooh, I don't know why I typed in a tan there. If you ever accidentally do something, you can hit the delete button if you hover over it. I had to hit back to hover over it, and then the delete button, and then I'll type it again. And from there, that's my equation. Let's get out of that second mode to quit out, go back to the main screen, get rid of that, don't need that. Now I need to take the integral of that. So technically, I'm going to do math 9, and it'll look a little bit different on the newer calculators. I'm going to take the derivative of which function, var's right, enter 1, the y1 function, with respect to x, from 0 to 3, and I get 60.257. 60.257. Oh, that's not an answer because we forgot to divide by 3. Divide by 3. And 20.086. 20.086. Hey, that's answer A. And yeah, I think that's all the homework. Just as a... No, I don't need to redo it. That's why we have a video. The end. Bye.